After schematics to Monday and not today. If you've already been working on it furiously, that's fine. We'll have more time. So what we're going to do is a live Gadget 1 assignment demonstration, sort of put everything together and run through the phases of actually capturing the schematic from a use case. Maybe we'll do some layout. Maybe we'll look at the build materials, some other stuff, and just figure out how to build a gadget. So if you've been struggling with Eagle, first thing I recommend is get a mouse. If you're trying to use Eagle with just a laptop touchpad, you're making your life more difficult than it needs to be. Okay, get rid of that. So here I've got my top quality Gadget 1 use case. I'm going to build a glowing temperature balloon. Maybe I'm cheating because I already brought one with me to make it a little, show you what it is. But basically, we're going to sense temperature, and then we're going to display that absolute temperature using color, so you can figure out, is it hot in here or is it just me? So if your room is saying, well, it's blue in here, it's actually kind of cold. Then you know it's cold in here, and you can go get a sweater or turn up the heat. But if the room is green or red or happy, and you're just really hot, then you need to not be jogging or doing whatever you're doing to make it warm. And not turn the thermostat down on everybody else. And then just for fun, this one doesn't have it, but I'm going to add in a 2-digit display to actually output the number of degrees. And maybe I can't hit 3 digits and show 100 degrees, but I don't want to be in that room anyway, so maybe it's okay. So what am I going to do? It sets the temperature, it outputs a color, to represent room warmth, as well as the numeric display. So these are just that, you were supposed to give all these little bits of information with your use case. So if you just gave us a paragraph of stuff, the TA is probably very grumpy with you. But if you gave them the ABCs, then you're probably much happier with it. You gave you check marks instead of unhappy faces. So what does it do? I can grab the assignment. Let our website wake up. So let's see. Deliverables. How does it acquire information? Okay, so it's going to blow. And it's going to use a thermistor. So it's as simple as that. And then what's the purpose of it? It's to keep people from messing with the thermostat on you, because the room's just fine. They're just really hot or really cold. You don't want them to keep moving the thermostat on you. So what's the environment? It's going to be any shared indoor space where you want to know what the temperature is. And who's it for? It's anybody who's in the space. So these questions seem really kind of boring, but you just write something down. It's pretty obvious, but clearly it's going to be indoors. We're not going to take it outside. It doesn't have to be in space. We're not putting it underwater. It's just going to be inside a regular room. And so it seems really obvious, but sometimes people need something that does go underwater or in space. And then there are all these extra things you have to worry about. And it's good to know about those ahead of time. So what's the sensors? The only sensor we have is temperature. And then what are we trying to relay? We're going to relay the absolute temperature. So we need to calculate that from a resistance. So there's going to be some math that our processor has to do. And then we probably want to make some custom temperature mapping so that it looks nice, right? Because you can't just say, my thermistor gave me a value of 138. Let me set my LED to 138. I don't know what that's going to do. It's probably going to be something crazy. So, if you think about it, you can play with the colors. Maybe you go look up those color temperature charts for websites. And just get a feel, and you say, well, blue is going to be cold, green will be some happy temperature like 72 degrees, and red is going to be something over 80 degrees. You kind of just work from it from there. You could spend 100 hours picking the perfect temperature conversion system, but that's not required for this class. You just want to have something with a little bit of thought put into it. So then the nuts and bolts, I'm going to use a temperature sensor. We're going to use a thermistor. Then I want to use 3 tricolor LEDs so that they're really bright. But they're going to be the same color all the time, so I don't need to have them independently controlled. And I'm going to have 2 digits of BCD display. How is it going to be powered? I'm going to plug it into the wall. And I'm going to use a 5-volt USB adapter to do that. And then what's the housing going to look like? I'm going to put it in a base with some big opaque things so that all the LEDs inside diffuse properly. So that doesn't look nearly as nice as having a big glowy thing. And when you're in a regular room and not a giant lecture hall, it actually is pretty bright. Plus this thing is kind of getting on in here, so the LEDs kind of get tired. Okay, so let's make a gadget. So I've got Eagle here. My Eagle's a little shinier than yours, but it's not the same. You say, oh no, what do I have here? Do I have a blank schematic? No, I want to start with where skeleton goes. Is that on the website?
It should be on the website. Yeah.
Sorry, I have two computers open. Okay, so you really, really want to start with this gadget for schematic. If you want to look at your own, it's excited.
Just refresh the page. Don't open the flash thing. That flash thing's dead. Just click down one next time.
So what's
Oh,
that flash?
now download.
I've got two downloads. All right.
There it is.
Okay. Okay, now I've got the edge core. All right, let's open that. I forgot something. All right, so here we sort of helped you out a little bit by just putting in this programming editor. Mostly we did this because we get very upset when people make their gadgets and then they don't have a programming header, because then it makes it very hard to program the gadget. So that's why that's there. So you want to make really sure that as you work on your gadget, you don't delete this, change the nets around, put reset to some different pin. So you want to avoid deleting these. When you're actually using your gadget, you are allowed to use these three pins and connect them to something else. It's just when you're programming, something funny is going to happen. Okay, so let's see. I need a thermistor. That was on my to-do list. So power input regulation, thermistor. Let me start with the thermistor. Now I could just throw down a voltage divider, or if you have no clue what you're doing, you say, well, I think somewhere in that lecture there was some voltage divider and a whole bunch of other example schematics. So why don't I just go to that lecture and keep it open? And so working here is voltage divider. So I basically want to build this circuit right here. And the whole point of your homework with Eagle was not to torture you by making you use Eagle, but to make it so you could do your gadget and capture this stuff. So you say, okay, I can probably make something that looks like that. So the first thing I'm going to do is add a thing. So first I'm going to do use, because I want to make sure I'm using the right library, which is somewhere hidden on my computer. And so there's this gadget group 2013. It's going to be in the same folder as all your other stuff. And then since Eagle is helpful, absolutely nothing will happen when you correctly use the library. Now I'm going to type add. It's going to calculate the first 10,000 prime numbers. Look at a bunch of other stuff, go on the internet. I don't know what that could be. And then eventually, it'll show you 30,000 libraries you're not supposed to use, and And then way down here in the G's, you can see there's one from 2008. We've got this other one. Here's fun with robots. That's a very old library. But here we go. We got gadgetry. So some of you have hopefully already looked at this. And there's a bunch of parts in here, some of which are a little esoteric, but maybe the accelerometer tells you what it does. There's the AT tiny, the batteries, point cell, button, a buzzer. These secret things sound fancy, but they're just connectors. But they're fancy looking connectors. So if you want something pretty on your board, there's the connectors. We also have these pin headers, which are sort of just these half-hearted connectors. They're like, here's some holes on the board. Maybe stick some pins in them. Whereas these are secret. You can go, Google them, Molex sells them. They have these nice little plastic housings with connectors to only plug in one way. But if you're just going to kind of mess around with something like a thermistor, you might just use a pin header and just solder it directly. So in fact, if I go down here, there's no thermistor. And so I say, oh no, what do? You say, well, I'm going to use the thermistor I got in my gadgetry kit. So what does it do? It has two legs. And I'm just going to solder it down to my board. So I'm going to use this pin header 1x2 because I want two legs. And then I got all these choices. I've got 2 millimeter metric. I've got 0.1 inch. I've got all kinds of crazy options. Here are some 90-degree ones, which if you look at them, they don't really change the size of the holes. They just put prettier pictures on your board to remind you that you're going to have this right angle header. I've got some surface mount ones. I have 90-degree angle surface mount ones. So of all of these, if I was going to stick something on my board that would have my little thermistor go through it, I probably just want this regular boring 2-pin one. So that's what I'm going to use. I'm going to stick it in my sensors. All right, so they call it JP1. I don't like that, so what I'm going to do is I'm going to name it I call it thermistor, but if you remember from doing your actual layout, when you have really long text, it shows up on your board and you're like, how do I rearrange this? So I'll call it thermistor for now. And then I need, let's just go look over at this thing. Okay, I've got my other, this one was much prettier, but it was a lot more ambiguous. So let's grab this other resistor. Okay, so let's do that. So we'll add resistor. There are a lot fewer choices. There are a couple true hole ones that we left in case we need them, but really you want to use the surface mount one, and then you can just tweezer it on. All right, so I'm going to have that. R2 short. And then what else did I need? It looks like I have this VCC and this ground thing, so let's add those. I believe those are not in your library, so you don't have, don't use our library because they're logical symbols. So I'll just type add GMD if you remember. There's one in SparkFun, so if you want to use the one that SparkFun copied out of supply one, you're welcome to. I'm just going to use it straight out of supply one. I'll stick the ground there, and then I needed a VCC, which is right there. Now let's just make sure that looks like the VCC over here. Yep. Okay, so now I've got that. And now if you remember, we got to make those nets to connect everything. So I'm going to use the net command. You can also use the wire command, but then you might forget and be on the wrong net layer. So I always use net. So then we just go here, connect it. My sound was on, it would make a happy ding sound, I think. Okay, so now I've made some nets. Yep.
When you get those little circles to show up, it shows you exactly where to wire to on the component.
No idea. They didn't used to have those. It might be something new in the interface.
I don't think it's on ours.
Maybe it's the professional version.
Okay.
Or I'm using the net command and not the wire command.
Yep.
I have no idea. That's a good question. All right, now I'm gonna, let's see, what do I need to do? I'm gonna have that, instead of calling it light sensor, I'm gonna call it temp sensor. And that was the name and label command. So I just typed them in. They're also hitting over here on this thing. So now I have this thing called temp sensor. And it goes from ground to VCC. That looks pretty good. Okay, so now I've got that. Now I wanted to get USB power. So let me go do that. I got this whole giant section for power. All right, that looks complicated. Surely I need a very complicated power connection. Let me just hit backspace. Find all the things possible. Now I'm just going to use a USB connector. All right. Okay, so now it's got this. Personally, I don't like the ones going that way. I'm going to type mirror. Flipped around for me. Now, there are these secret extra grounds here. Those are there to trick you. Don't actually connect your grounds to those grounds. Those are the shield grounds on the actual metal chassis. You don't want to connect those on your USB ports. What am I going to do? I'm going to do V-bus, ground. Now, from this connector, I'm expecting 5 volts to come in. And if I can trust it or I can not trust it. If I trust it, then I'll do what I'm going to do now. So I'm going to add some power and ground. So I'm just going to copy these VCCs and grounds because I'm lazy. And I'm going to do this. And so I'm just going to trust that VCC is going to be 5 volts and it's going to come from this USB connector and everything's going to be good. If somebody decides to hook up 12 volts to your gadget, it will explode. Or if your power wire is bad or you decide to run it near your blender and the voltage fluctuates, your processor might go crazy for a while. It's like 5.7 volts per year. You know, who knows what's going to happen. So you could also have a regulator. But for this gadget, I'm just going to have it plugged directly to the 5 volts. Or if you had sensors that needed 3.3 volts, you'd have to do 3.3 volts. So let me just do it this way. But what I am going to do is go down for little example circuits. Buttons. Power over USB. So here's a regulator. What I am going to do is I'm going to, and you'll notice over here we don't have those connected. So there's an example circuit that is not connected. I really like having that 10 microfarad capacity because that makes your gadget not crash. So I'm going to add that capacitor. So I'm just going to go over to capacitor. And you notice that there's a small one and a really big one. I think you can tell the size difference there. For this kind of stuff, you can use the small one. If you're doing any motor power, you may use the big one. Motor or large servos. And for just microcontroller stuff, you're probably fine. Okay, so we have C1. And I'm going to connect it. And I'm going to use the value command because I wanted this to be 10 microfarads. And there's no special micro key. We just use U, lowercase u. Yep.
The capacitor just stabilizes the voltage, right?
Correct. So it's sort of like the mini UPS. It prevents random fluctuations because you're right, we're going to have a 6-foot wire. You know, when the microcontroller wants to do something, 5 volts is coming from way down that wire. You want things to not like brown out and reboot every time you blink your LEDs. That would be bad. Okay, so let's look at my to-do list. I got my power. Do I want regulation? I'm going to say no. Maybe we'll come back and look at how you put a regulator in there. Usually they're a good idea, but if you're going to do something like, you'll notice your mini gadget does not have a regulator. And that's because we say, well, the battery can only provide somewhere between 3 volts and 4.5 volts. There's no way we're going to get 11 volts out of this thing. It's probably okay. And same here, I'm saying I'm going to plug directly into the USB port. I'm probably going to be okay. Maybe my gadget explodes, but if it did, that's probably because I did something really bad. And we can talk on Gadget 2 on how you put more protection and stuff in to prevent people from doing bad things to your gadgets. Okay, so we got my high-tech to-do list here. I've got power input, done. Regulation, we're going to say no. Thermistor, on or off board. So the way we have this, we just have this little connector. We could be on the board or off the board, right? Because I could either solder the thermistor directly in, or I could put a little header there, kind of like what you guys plug in your USB port, and then I could run wires to a thermistor somewhere else. You know, because maybe, let's say that wall board, all that heat generated was right next to my thermistor. That would give me a very accurate picture of what the room temperature was. So I might want to move the thermistor far away. And if you'll notice, on this little circuit board, these LEDs do get a little warm, and so the thermistor is hanging out way down here, just sort of on the longest legs it can, just sticking off the board. Because they do sell board mount thermistors. They look like a resistor because they are resistors. But this way, you know, we're kind of getting it far away. And you know, this is where it helps to start thinking about your housing and sensors. You know, obviously, if you have an ambient sound sensor, you probably don't want it fully encased in your housing with like extra sound insulation. It's not going to be very useful to you. You're going to say, well, I kind of want that on the exterior of my bedroom. Okay, so I got temperature sensor, not an off board, but the button and potentiometer. Sure, let me add one. I like buttons. Because maybe when I'm doing my programming, it'll make my life easier if I can hit a button to like cycle through my colors, rather than having me squeeze the thermistor all the time. All right, so there's a button. So let's copy and paste. Let's see, somewhere back here, I've got a button. Too easy. There we go, buttons. Pull down or pull up? Anyone care? Yeah, all right. I will do a pull down. Okay, thank you. I can talk about registers instead if you guys want. Okay, I'm going to put this resistor in here. If you want to get lazy, there's another way. If you connect the two legs, it creates a net for you. And then I can create another net there. So there's another lazy way to make nets. Get tired of drawing those little nets. And I can do the same from there. So I've got my button. So when I press the button, it goes to VCC. Otherwise, it goes to ground. I just have to connect the actual net. All right. So I'm going to call this one button. Okay. And let's add a potentiometer. There's a couple shapes. This one looks enormous. It looks like it's 6 inches long. I'm trying to think of what project needed a 6-inch long linear slide pot, like the kind you have on like a mixer. But you know, you can buy them for $10 and stick them on your gadget if you have a use for it. But I like this one, which is just a little thumb wheel. And the way it's meant to be used is those two upper holes are mounting holes, and you want that other part of the circle to stick off the edge of your board so that someone can just, you know, wiggle it with their thumb. So I'm going to use that one. All right, so this one looks complicated. How do I hook it up? Let's go look. Let's see. This is even easier. I just have to connect power and ground, and that middle arm is where the middle value comes in. That. So again, I'm lazy, so I'm just going to copy and paste my VCC and grounds. And I'm going to wire come out, and I'm going to name this one pot. Okay, so now I've got 3 input sensors. Let's look at what else I wanted. Oh, right, I need LEDs. So there's a couple ways we could do LEDs. The LEDs on your mini gadget are kind of awesome. Here we go, RGB LED. So if you want crazy bright RGB LEDs, you can do no better than this. Tom sort of stays on the state-of-the-art of LED technologies. So addresses on that one. 30 cents to $1. Depends on how many you're buying. If you've ever seen those RGB LED light strips. They basically just have like 50 of them per meter. It's going crazy. Okay, so here I've got this. Now I got to drive this thing. How on earth does that work? Let's see. Actuators, LEDs, full color LED. Okay. We got these. So red, green, blue. I'll do it this way because I trust this way better. Okay. This. Now, do I want to rename that? The answer is yes, because I want that to be power. And then net. Voltage common cathode versus voltage device stack. Let's do basically, there's a lot of old technologies, and they varied on what they were. There's also ground and ESS. They're sort of synonymous. In our Eagle schematics, what we use them for is to denote different supplies. So I'm using VCC as my logic power. If you use VDD but we're consistent everywhere, I don't think anyone would even make a comment on it. We would just say, okay, you're using VDD, everywhere your power is VDD, that's your logic power, that's fine. You could also, if you really wanted to, let's see, add 5V. There's all kinds. Like if you said, I'm using 5 volts, I'm going to use plus 5V, that's going to be my supply. You know, down it comes. You just want to make sure you use them. You don't want to just rename them because that doesn't actually do anything. Like I could name this, Mr. McGillicuddy, but that doesn't actually change anything. I could change this to Mr. McGillicuddy. That's hard to say. So now I've got that. Is that my new voltage, logic voltage? Maybe. It could be if you want to be consistent. But the thing is, it doesn't rename the trace. That's still called VCC. So you can't just rename those things and think that something good is going to happen. You'd want to use the plus 5 volt, or you'd have to go through and name them all randomly. But there are a lot of different conventions. We're just using VCC because it's simple, and most of you only have one voltage. Or you might have a battery voltage, which we call V battery, VDD, and then regulate to VCC. Okay, so now I've got this. And I'm going to name this one blue, and I believe it's not blue. Let's see if I got that right. Because that very cool bar on it. I'll call this one the green one. And, all right. Okay. So something that I have not been doing that you should be doing religiously is anytime you add a little bit of stuff, you want to be typing ERC. Because ERC will start to generate errors based on you doing the wrong thing. And it's really disheartening to do your whole thing and then find you've been doing something wrong every single time. So that's bad. And a lot of these can be real errors. So here, net VCC overlaps pin. It's like, oh, I know what I forgot to do. I forgot the junctions. And those are very good errors because there are other errors that give the same warning but have a very different problem. So you want to make sure you just get rid of all of those. So let's see. Only one pin on blue. Well, that's okay for now because I haven't hooked it up to my microcontroller. Only one pin on green, only one pin on red, only one pin on pot. Part ISP has no value. I'm sure all of you guys ran into that. What I usually like to do is you can just give it a value. If you wanted to be fancy and save yourself some time later, you would put in like a part number so that when you go to buy it, you say, oh, let me just see, this value is this part number that I can buy it. Or you just put ISP so it stops complaining at you. That's okay too. R2 has no value. Well, that's bad. I kind of care about that one. I'm not just going to type R2. That doesn't solve my problem. I think from the example circuit, it called for 4.7K. If you are interested in these kind of values, you can ask us where these came from, and we can talk to you about selecting them for different things. What you can play with is basically, with this voltage divider, you buy a thermistor which has a variable resistance, and then you see how much dynamic range you have. If we got a 100 kilo ohm thermistor, this would not work very well because the value of that 100 k ohm resistor would change a lot, but the ratio between the two would not change a lot. So what we usually do is we take 4.7K here, and then we use about a 4.7K to 10K one there, and then we end up getting a reasonable resolution, maybe 6 bits. So you say, well, I can probably tell temperature to a degree or so, which without fancy calibration is probably good enough. Yep.
When you use a thermistor, do you have to calibrate it yourself?
Yes and no. You don't have to go get yourself a clear IR meter and like get it perfect. It's all about your use case, right? If you're just going to display temperatures, I don't think anyone's going to like come banging on the door if I'm off by a degree or two. And if you're doing something where just there's a too hot temperature and a too cold temperature, you can just calibrate those experimentally and say, well, it's too hot when the thermistor reads 82, and it's too cold when it reads 200. So there's my values. I don't care what the resistance was. I don't care what the absolute temperature was. I just experimentally used my gadget to determine the value then. So that's why, you can stress about whether this is the right value for you, or you can just use it and not worry about it. And at worst, you remove the resistor and put a different one. Okay, so what other errors did I have? R3 has no value. That's a button. I think we said 47K for that. And part therm has no value. Well, now we know. Let's say it's a 4.7K thermistor. Okay. So these errors are fine because I know I'm not done hooking it up to my microcontroller. Yep.
So did you do the not bar?
The not bar. You use an exclamation point. So it's not blue. It's exclamation blue. Doesn't mean it's exciting. It's not Spanish. It's a logical not. And the reason we have this is because if my microcontroller outputs a high on that pin, it will be VCC on both sides, and no current's going to flow. So we say it's off. And then the asserted state is low, so that when I assert it, it's going to be blue. And then I have 0 volts here and VCC here. Current's going to flow, and everything's great. That's what the not's for. Yep. Historically, it is always better to sync current. The other detail, when you're buying other LED devices, they almost always are in a common anode configuration where they only give you 4 pins. And you get the low side of each, and then you get one common power pin. So for instance, if I wanted to buy an RGB LED light strip, which is super easy to use and interface to, they're almost always common anode, like this. So some detail. Now I've done all my ERC and I have no more errors.
Question before you leave that part.
Yeah.
Can you hook several things in parallel? So several LEDs in parallel and use the same, not blue, not green, not red, and VCC?
Yeah. Here.
You don't have to do it. I just
Well, I wanted 4 LEDs, right? Or 3. I think I said 3. So remember the secret cut. So I've grouped it. I've typed the cut command. Now I'm going to do control right click. You just have to remember that. Now I'm going to use paste, since it didn't actually cut it, and I'm going to use paste. And there we go. And I've got 2. And I've got 3. It's madness. I can keep going. I can group all 3 now and have like 12, 16, 87. There's some details, like my board would probably melt or just not turn on. And there's something else that I've forgotten. Does anyone know what I forgot? Well, I do. So my ERC is happy with everything I've done. And you'll also notice that now it says, oh, you don't have to connect blue, green, or red to your microcontroller, because now there's multiple things. They're all connected. It's great. Yeah, so there's another one of those secret errors that it's a logical error it can't catch. The other thing it can't catch is I don't have a current limiting resistor here on any of these, so the microcontroller is going to basically be a short circuit all the time, which your microcontroller is not happy about, so don't do it. Now, if I had just been copying and pasting, I probably would have been okay, because right here, what does it tell me to do? Put those resistors in. So if you put the resistors in, you're not going to have a problem if you copy the example circuits. So there's something I forgot. So let me, so what do I have to do? I have to say, well, let me just delete those, it'll be faster. And let's see, I'll delete those. And if I could just add the resistor, or I could say I'm lazy, I'm just going to copy that one. And copy it a couple more times. And then let's look at the values. I needed 22s on blue, which is rich green, and 68 on red. I'm not sure those are actually red anymore, but we'll get back to them. So let's use 22, 62, and 68. If that angers your inner OCD, you can use the smash command so that we can move these labels so they don't interfere with each other. That's a little more readable. And then we just have to make sure we clean it up. Okay. All right, so name. We got blue, green, and red. Okay, now let's check our ERC. Still the same errors, so my errors haven't changed, but now my circuit's going to work. So these are scary things. That's why we tell you to submit your schematics. You want to put as much as you can so that we can try to help you catch those things. All right, so now I'm going to group this, cut it, and paste it. All right, so now I've done this, and I've got my 3 LEDs. And let's see, what else did I have to put in my gadget? BCD hookup. All right, that sounds fun. Now, I'm kind of already running out of space, so I'm just going to make this thing bigger. BCDs are a little esoteric, but there are actually a surprising number of you who really want to have decimal digit display. So we've added them to the library. So, okay. So now I'm going to go back to the library. Cache tree. And what the heck was it called? Aha. BCD to 7 segments. Now, why do we have that? And that's to drive the 7-segment display, which looks like that. So I think a lot of you guys have seen these things. So here's a little LED display. It's got a bunch of pins. And so rather than having to hook up to all those things to your microcontroller, we're going to use a BCD converter to save you pins. Because pins are a precious resource on a little tiny 85s. So we're going to use this and the 7-segment to sort of put it together. So let's do that now. Got that. And let's add in, lost it already. There it is. Is this crazy thing? Oh man, does that just light up? Oh, that's nice. Let's just do that. I'm going to do that to make sure the wires connect. So I've got my A, B, C, D, E, F, G's all hooked up. And you'll notice right here, right? CA. Again, it's common anode. So everybody expects you to have your LEDs hold high, and then you ground them when you want to drive them. So that's, I think, is the decimal point. So alas, our BCD will not have decimal point technology. So that will just stay on top of it. All right. All right. I'm going to remember this time the metal junction. Let's see. Oh no. So angry. All right, well, that probably wants power. Power. Now, also the reason I'm doing this, BCD displays, this is also going to sneak into your example circuits that you're going to be able to look at. Yep.
Do you have to set one of these up for every digit you want to display?
Yep.
Okay.
That's what the group cut, copy, and paste commands are for. Now, something we I don't think we've sort of beaten into your brain, but anytime you have any sort of intelligent chip with legs, you need to put your own, a deep coupling capacitor on its power supply. So I'm going to do that right now. So not optional. It sort of keeps your things from crashing. It's very frustrating to debug why your thing works when you display 0 through 7, but as soon as you try to display an 8 or a 9, your whole device resets. No one wants to have to figure that out, especially when it turns out putting like a little part fixes it. Okay, so we got all these scary labels. Well, I'm going to just assume I'm going to have to connect all these, so let's just do that. Got things like LTBI and LE. Let's see, if only I had the page set up. So here we go. If you care about this kind of stuff, then for Gadget 2, you're going to be on your own. But basically guaranteed 10 million drive capability. Pin description, lamp test input. Maybe we don't need lamp test, and we just sort of trust that it works. Ripple blanking input, are you guys worried about ripple blanking? I'm not. Latch enable, that sounds important. I think the latch makes it go, so let's make sure we have that. The BCD address inputs, I think we need that. Yep.
Is ripple blanking where if you have a whole bunch in a series, it blanks them all by one?
You want to turn them off so you don't see them sort of shift from one to the other. So let's say you had 100 in a row. It's going to take you potentially a couple milliseconds to change them all.
Oh, the ripple blanking just means they're blank until it gets to the last one.
So for those of you who are interested in electrical engineer sorts, they give you a helpful truth table. This is all possible things this thing can do. If it's making your eyes bleed to look at, you may not be an electrical engineer, and that's okay. But basically what it's saying is, if you have the blanking, it was BI, that was the ripple one, right? So if BI is high, the thing works. If it's low, nothing happens. The display is blank. Doesn't matter what everything else is doing. That's what the X is doing. Don't care. Also the LT one. If LT is low, it displays an 8 at all times. So if you really just want to display an 8, you could get away with just having one pin hooked up to this thing. If it seems a little strange to me, let us know. Hey, you can click 8s. So otherwise, this thing, when it's high, it does not flash an 8. Except in the 8 case, but that's because of all the other stuff. So I'm going to say that the LT thing is something we don't need ever. And I'm going to connect it to VCC so that it's always high. You can use a supply bar if you like, but here I'm just going to use typing VCC. Okay, so that one pin down. BI, blanking the display. If you want to be able to blank it, you can use it, but I don't really want to ever use it. So I'm just going to also hit this one, the VCC. Okay, but latch enable, let's see what happens. Latch enable is low, it displays. Otherwise it's high to low. I guess it leaves it alone. So we could actually ignore the latch. So for those of you who are interested, if you were back in the 80s trying to like make a product using these and like you wanted it to always be nice and work well, you have basically have the decoder of the drivers. So whatever the decoder sees, it's going to display that digit. And so the latch allows you to sort of load the next value before you're ready to display it. And then when you toggle the latch, it will do something. But I don't think I really care about that, so I'm just going to leave the latch low. So latch enable low. So name ground. Now you can think deeply about whether you want the ability to flash 8s or blank the screen at any time. But I'm just going to say that we don't actually need any of those pins. And we're just going to do that. And now, I'm gonna name this one, I'm gonna call it BCDA. BCDB. BCDC. And BCDB. Now, and I don't know if you saw the little table, but basically, depending on your 4 inputs, if you give them a 0, 0, 0, 0, the display will display 0. If you give it 0, 0, 1, you'll get a 1, and then you'll get, it's basically converting from binary to decimal. That's what BCD stands for. So that's what it's doing. Okay, so now I've got that. Now, is there anything else I haven't forgotten? Oh yeah, remember those resistors? I bet this thing also gets angry when we short circuit. So let's delete these wonderfully convenient lines. And now, put some resistors in place. And that looks pretty awful. And if you tried to give us that, we'd probably yell at you for having us look at what looks like angry bumblebees in a sweater. So, don't do that. Try to make it readable. Or we're going to punish you by making you tell us exactly what your gadget does. And you're going to have to use only your schematic to do so. So do that. And then move these out of the way. I'm going to leave these alone as angry sweater for now, just so that we move on with our lives. Only input pins. Oh no. So that's angry at us. And then we got these only one pin on net. And we get these weird ones that's saying power VDD is connected to VCC and ESS is connected to ground. If you get these, it's sort of telling you that you're sort of mixing your technologies, or you're mixing your metaphors. It's saying you're mixing your metaphors. That's really annoying. Why are you doing this? And these are the only kind of errors that are okay to approve. Approved errors no longer come back when you type ERC. They're hiding here. Don't just approve all your errors, because you can also look specifically at your errors by doing it. So if you just have like 87 errors on your board and you just approve them all and submit it and hope that when you type ERC you get those errors, you say, oh, your board works great. No, you can check those. But those are the sort of ones that you can approve. Okay, so now I've got my crazy LED. I've got a bunch of resistors that really need to be made pretty. So now I've got to hook all this up to my microcontroller. So let's do that. So the thing I care about most is the temperature sensor. And I feel like ADC0 is a good place to put it. So we'll call that temp sensor. All right. And how about the potentiometer? That sounds good too. All right. I think we have a button. So I'm just using name and label here. And how about over here is we'll put RGB. Now, there is the OC01A and 1B. I can do hardware PWM, but I'm just going to do soft PWM. I think that'll be fine. So I'll just put red. Now notice their thing was in blue, green, red, but I don't have to do exactly what the part says. I can put them in a way that makes sense to me over here. And that's why I put ADC0 as my temperature sensor, ADC1 as my potentiometer. Okay, and now I need to hook up BCD, A, B, C, and D. It's like, uh-oh, I've only got 2 pins left before I run into things I've already done. So let me do A and B first. Let's see. So reset you have to leave alone. Reset cannot be used for anything else. But these other ones are reusable. So what I'm going to do another net. I'm gonna call this BCD. And then I'm gonna have to share these nets, which gets tricky. So, and the reason I'm putting it here, for those of you who love your binary to decimal conversions and digital logic, I'm gonna use the upper nibble of port A for my BCD, which will make my code slightly simpler for those of you who like writing low-level code. But you can use any pins, and we can help you make a function to convert. It's pretty simple, and we'll explain it more fully later on. But what I'm going to do is I'm going to change this. I'm going to call this SCK/BCDA. And did that change it? No, that was very bad, because that's still SCK. And that's what I did not want to do. I did not want to break all of my ISP heads. So I'm going to try that again, and I'm going to do every segment of the sheet, BCDA. And now I checked over there, it's still good. And now I'm going to go over here and do the same thing. And I'm going to do SCK/BCDA. And it says, do I want to connect them? Yes. Okay. I do the same thing here. MISO/BCDA. Every segment. Over here, MOSI/BCDC. Oh, I screwed that one up. So it looks pretty ugly, but it helps everybody see what you're connecting to, because you're going to two places. Because it's not as clear when you just say, oh, I'm just going to connect MOSI to IC and IC2. That doesn't really tell me what on earth's going on. Like, why is MOSI going over here? Is that because you're using the serial peripheral interface? I don't think so. Okay. Now let's see what we get. Errors, no errors, that's great. Now the two weird issues about VDD being VCC and VSS being ground, which is just, two conventions that we're mixing. If I had made my entire board using VDD and VSS, that error would have shown up. Okay. Kraus, you have anything to throw in? I've got my gadget.
Let's see, making the numbering things, that they're not dollar signs.
Oh, yeah. I don't know about you, but $3 is terrible as a name for an LED. I'm going to call that LED1. Maybe that one will be LED2. Over here, that looks prime for LED3. Now that makes a lot more sense. We got therm, $1, like, you're like, what was I thinking? Why don't I just call it button? $2, I'll call it potentiometer. Display 1, that's not bad. IC2, that sounds fine. Okay, and let's look at this. How about USB 1? Sure. I don't know if I have a USB 2, so maybe I'll just make it USB. Okay, so that's one digit. Now, if you need 2 digits, this is where you start caring about these other lines, because what you could do is use the blanking. You could use the latch enable, and if each one you have the latch enable set separately, you can set the latch enable high on one you want to leave alone, modify the other one, set its latch enable high, and then go back to the other one. Because when the latch is high, no matter what you're doing on those input pins, it stays put. So if you need 2 or 3 digits, you just have to basically account for 4 pins for the BCD, and then you need 1 pin for each extra display, so for each display. So if you have 2 digits, you have 6 pins. If you have 3 digits, you have 7 pins. If you have 4 digits, you have 8 pins. If you have 5 digits, you have 9 pins, and you can make it work. So without getting too rough. Now, if I had got way too many and I needed like 2 more pins, maybe that's when I start saying, do I really need a button? Do I really need a potentiometer? Those aren't even in my use case. I just sort of threw those in because I'm bored. So, maybe I don't want to actually do those. Okay, so now that I've got this, my ERC is happy. So then we could look look at layout. All right. Oh no, I don't have it. Should I create it from Schematic? I'm going to say no, because the first thing I'm going to do is I'm going to save this as not gadget core. If you submit gadget core, it only works for one person. When we have 37 gadget cores, we get very upset. So I'm going to call this glowy orb, or maybe be Kirby, because otherwise my key is going to be very angry. Right.
Wouldn't it be great if you put some text onto your schematic that
Oh,
had
man.
the name of yourself and the thing that you're making?
That's outrageous. Glowy LED orb. That's way too small. Let's gigantify it.
Let's also make it not a wire. That's also-
Yes, I'm in the names layer. Glowy LED orb. Depending on how late it is, you might have similar comments. Oh, well, what I would do is I'd go find one of those, and I'll copy and paste it.
So if Eagle comes with some of those, they're in the frame supply list. Now, the biggest caveat of using those is that they are very often not the size that you happen to need. So you might end up cramming stuff in to try and fit it, or you end up with a lot of empty space. So that's one reason that doing just boxes, which is a lot simpler,
Yeah.
would be useful.
Now, these blue wires that are here, they're not particularly magic.
I don't think
The script.
it's
So we just made these, and like you go over to style, you can do long dash, you can change the width. I mean, you can go crazy with these things if you want. So if you want to make your own little box of fields, I mean, you can make things arbitrarily pretty. Eagle is fundamentally not designed to make anything look pretty, so I'm not going to worry about it. But you definitely want to have things like, maybe that's too tall. Let's just
font size is better.
so I can shrink the font size. So we didn't put that in your gadget core. This is, help us identify it. Something I often do also, you'll notice that I was looking at this to-do.txt, which totally has the next things I'm going to be doing. Sometimes I actually put these directly in the schematic. Say, add LEDs. And I put it in my actuators. My actuators are blank. I just add LEDs, and then when I finish adding them all, I just delete them. So I do that pretty frequently, just because then I don't have to alt tab 37 times. Okay, so now I've got some LEDs, I got some descriptions. Not go to Cam. Word button. Do I want to create? Yes. Okay. So now we're at this stage. Where we say, oh, I want to put this stuff. And we want to have the LEDs. What? Well, that's what happens when you use binary to, BCDs. You need a lot of resistors. You could also use one resistor on the common anode, but then different, depending on how many LEDs are on, it's brighter or dimmer. This is the more appropriate way to do it. Yep.
Is there some sort of device which would allow you to use even fewer pins to run the 7-7? Like, so you don't have to use a separate port for each segment of the end, or for
Okay,
each digit?
so why don't I very briefly, if I needed to do, I'm going to do 2, 3 works exactly the same. So going from, with 1, I can get away with just 4 pins. For 2, I need 6 pins. 3 is 7 pins. So the way that works is I do this, grab, no, not that. I grab everything, paste it. I think I even said I was going to use 2. So, okay. A, B, C, and D can stay the same, but then latch enable I need to change to latch 1. And then only this segment. And over here I'm going to change this to latch 2. So now, when latch is low, that display is changing, and when latch is high, that display does not change. So by toggling the two of them, you can do one or the other. And with 3, it works the same. But now I have to figure out how to put latch 1 and latch 2 in. So net, let's throw this here. Oh, I've got a long dash line. There it is. Now notice if you're using the wire command, it's going to default to whatever crazy wire I was using last on the wrong layer. Okay, I'm going to call this one latch 1. Connect, yes. And again, it changes your sizes. So now I'm in the pickle where I say I have too much stuff. What do I do? You do not get to share reset. Reset is not allowed. Otherwise, you'll reset yourself, which I think you can do. And that's bad. We don't want to change B, C, D, A, B, C, or D, so now I have to start throwing away features. So maybe I get rid of the button or the touchdown. Anyone want to vote? Button, touchdown there?
Button.
Button, all right. Everyone hates buttons. Fair enough. Okay, the button is gone. I'm going to name this, actually I'm going to name this button latch 1 again. Because it bothers me to have latch 2 instead of latch 1. Okay, so now I got latch 1, I got latch 2. Double check my ERC. Oh no! I got more of these errors. Let me improve them. You really want to make sure that you have no ERC errors before you go to layout. It's also good if you sort of avoid logical errors, like I forgot all my resistors. So now let's go back to our board. Oh no, we have more resistors. And here we go. Now, and then you get to arrange things. And then things like the potentiometer, remember, you kind of want to sort of have sticking out the side of your board. USB does not work if you point the business end of it in the middle of the board. You can't like plug it in. It has to be sticking out the side, basically flush with the board. Maybe a little over if you're paranoid. No, this is the where your legs solder. So you have, this is one of the most common things is, here's this drawing. You just trust us that it's the right drawing. If you never go to the data sheet and like see where they have like the 3D model of the part and how it corresponds to this thing, you might just say, oh, that's where all the pokey bits are. Surely that's where I plug my connector in. But no, that's actually the legs on the back of the plant. So if you look at your mini gadget, you'll see, right, these are where the pads are to solder the part down, and the business end is right here. Or did we not put USB on this one? Never mind. That doesn't help you. So if you have a question about how a thing has to be connected and oriented, you should ask, because it does matter. And you will be very miserable when it's sideways.
Another question about orientation. What's the best way if you're like trying to make your or your board to some exact dimensions because you're like making a case for it? What's the best way to set dimensions precisely, or do you just have to look at the numbers and move it until?
Okay, so what I do, let's say we're going to be nice to ourselves and we're going to use like inches, and it's going to be some quarter inch. So I'm going to say grid 0.25. I'm going to turn grid on. Here's a quarter inch grid. So now, and I'm going to control click to snap everything on. Can you not see the lines? Cool. The projection is not like my grid lines. Fantastic. But if you type grid on, it'll show you a grid. I don't know how to make the grid lines stick.
Just grid with no parameters, so you can pull some dialog box. Yes. And so here you can set things, and you can also set, I think,
Display on off.
I think the finest might actually set the thickness of the lines, right, on the array. Oh, no, that did something wrong.
Do not
Don't do
use the
that.
finest. I'm going to go back to quarter inch. But there is a grid, and that's how you could make things pretty easily.
Yep. So that white line there is the size of your board, which we will
Yes, use the white line.
manufacturers will use too. So you want, at the end of the day, all your parts should go in there.
Well, I was just talking about like lining up buttons and stuff. So like if you want a button coming out of your enclosure, you know exactly where.
So let's say you drew it up on paper. You know your button is exactly 1 inch in and 1 inch over. wait, we don't have a button anymore. Let's say your potentiometer is gonna be exactly 2 inches up. We can just go to the part, and here it is. It has a position, 0.5, 1.3. So I'm gonna change that to 2. And there it goes, it jumps. So if you know exactly where a part should go, you can do that. Likewise, let's say, you could do some very interesting things, like, okay, let's say we have these LEDs. Let's say that's gonna be the center of our gadget. I'm gonna do some crazy rotation. Because, you know, who wants just 3 LEDs kind of thrown in the center half-heartedly? I want them to be at an angle. And if I do this enough, maybe I'll get the right angles. Let's try 45. I think I missed something here. I think this one has to stay straight. It's starting to make it look better. I don't know if that 1/4 inch grid is quite right for that. Clearly I can do something better there. But, right, there are other things that can make this stuff look cool. So if I'm gonna have like the orb, it's gonna center right on that spot. There's also nothing, I believe, I'll have to check with Tom on this, but we may let you use non-rectangular boards, depending on which board house we use. We'll let you know late in the game, so if you need just a round board or some funky board, let us know. You can still do it, you just have to put it in a box. So my recommendation is do your funny outline, but just put it in a box, and either we get it routed for you, or you're gonna have to like do it yourself with a belt sander or something and a dust mask. But you know, you can do that, and then you lay out everything the way you like it. Now, something here that clearly I haven't thought very hard with the gadget is how on earth do I have digits inside a glowy LED display? So like, I don't think I thought too hard on it. Like, something has to change. Either I have to have a funky board where maybe I have this longer section down here. So it's a glowy orb up there, and down here there's like stock. So this is the split command. I think we told you that it exists. Right, so you can do all kinds of funny stuff with your shape. In Eagle White, it'll yell at you if you're not within your little 80 millimeter by 100 millimeter box, but you've got 80 millimeters by 100 millimeter photo. So now you can imagine, like, this is the physical thing, right? I know what I want it to look like. I'm going to stick this thing over the top of that, and then there's going to be this crazy, like, little diving board sticking out with my digits. And since I have that, you know, you say, well, maybe, you know, I'm not going to stick the potentiometer over here. I'm going to stick the potentiometer over here on my little diving board so that you can get to it. But then all of my other Ghibli bits are going to go over here. And, you know, something else I might say is, well, my LEDs are going to be on the top, and then I'm going to put like a flat sheet instead of this giant orb. So maybe I want to put all my other stuff on the bottom so that it doesn't get in the way.
What did you get?
I used the mirror command. I got my ISP header, which I'm going to put on the bottom because that's really going to interfere with my LEDs. I could also move everything and mirror it all in one go. things on the bottom. So you can do this. However, for your gadgets, what we're going to ask you is, right now my complicated side is the bottom. We're going to ask that it makes our life much easier when you make sure your complicated side is the top of the board. So that if you want to do something funny like this, what we ask is you do it the other way, where you say, well, now in my head, I know the bottom of the board is the top, but the top is my component side. That's where all my parts are going to go. And then you need to make sure you mirror your displays. The potentiometer stays on the bottom of the board, then I leave it as is, or I can mirror it. In the case of the potentiometer, it wouldn't actually matter which side you soldered it into, but these things, you can't just leave them on the top and then flip them around. It just does not go. Right? You can't just flip everything around. You have to use the mirror command so that it works correctly. Whereas this thermistor, right, it has two legs. It's a resistor. Which side of the board the part is on doesn't matter because it doesn't matter. But for other parts, it generally does. So that's some fun we can do with the layout. But we're going to get to layouts. What we want for Monday is we want your schematic. We want you to get to this level where you say, hooray, here's my schematic. It's as good as I can get it. I have no errors except for when I'm using BCD. We have some errors in the library. I have my power figured out. I've basically done everything in my use case, because what is your TA going to do? He's going to go look at, he or she is going to go look at the use case and say, here's what you said you're going to do, here's your schematic. Does it do it? Yes or no? And go from there. And if you have errors in your implementation, we'll figure out what happens.
If we're changing up like a few small things, like we wanted like an extra LED or something, should we like send an email to the TAs, or should we just?
You should demarcate it clearly in your, like, here, I could have this, I could have the changes from use case, and start having this whole section where you start changing your mind. And it's okay to change your mind. You may find that having an orbital depth laser turned out to be more expensive, and you don't want to interface that anymore with Gadget 1. And that's probably okay. There are lots of ways to do the same thing.
Did we get any feedback on our use case at all?
You should have. I think we sent out that like a week and a half ago. I think we sent out another email saying, if you've not gotten use case feedback, please let us know immediately. So are you not on our gadgetry mailing list?
Let me check. Yeah, I'll look at it.
Okay. But yes, we should have feedback on everybody who submitted something. Yep.
For grading purposes, there's a couple things I wanted to leave flexible to do after this project turned in, but they're not going to be used for my,
So you can add, so.
just mark it and say.
Okay, so for Gadget 1 schematic, normally your TAs are merciless graders and grade for correctness. For this, what matters most is you told us what you were going to build. You now need to build it. If you make some errors in your schematic design, that's okay. Unless you're an engineer who does this every day, like, that's fine. Like, we may give you, and you're going to get a bunch of comments back. And they're going to sound grumpy because they're going to be real short. And they're going to be like, this is wrong, this is wrong, this is wrong, this is wrong, this is wrong. But it's really just, it's like the compiler giving you a bunch of errors, right? You hit compile by giving it to your TA and us. And then you're going to get a bunch of errors back. And then you need to fix them all or ask what the heck. Great, this is nice because there are actually human beings on the other side. So you can say, I don't know what this error means. What are you actually telling me here? And when you say no resistor on LED 1, you can say, oh, I didn't add the resistors like I was supposed to. Right, that's what we're talking about.
But specifically, what I was talking about was there's things that I don't think I'm going to get to during this yet, but I'd like to play with it after.
You'd like to add them on?
I would like to add a servo, but I don't want it to be used right now.
Well, you just have to say bonus feature.
Okay, well,
That's fine. You just want to make sure that everything in your use case is covered, so that because they can say, you said you're going to deploy, here it is. It's usually super obvious who's put effort into their gadget and who has not, which is independent to who has a correct working gadget and who has not. Those are two different things on different axes. And what we care about is that you put effort into it, trying to solve the problem that you gave us, and then we can help you get it technically correct. Because usually, it's just as simple as, oh gee, add some extra resistors, We'll try to make this available so that you can copy and paste this. It's probably right, I'll probably double check it. Things like that. So just make sure you submit the right thing. And you're gonna get feedback back. And one of the things that, for instance, on this design, you get some grumpy things saying, too many LEDs for 3 pins. Right, because this is not gonna glow very bright. Right, your LEDs are meant to draw crazy amounts of current and blind you. We're driving one of those LEDs with the pins. You can't drive 3 of those LEDs with one set of pins. And you panic, and then if you're lucky, someone will tell you, you should be using the motor big loads thing, which looks scary, but you're gonna say, wait, all I have to do is put this MOSFET in my circuit, and then instead of being underscore blue, I put blue here instead of exclamation point blue. And then when I turn this on, this switch lets my LED float, right? Because the LEDs are hooked up this way. So that's why I hooked them up that way, just so that you can sneak these MOSFETs in. And these MOSFETs, even the super tiny ones that are really annoying to hold with tweezers, can handle like 5 amps nowadays. So your 3 LEDs are fine. If you wanted to do giant 5-foot long strips of LED light strips, you'd give it 12 volts, and then you just use 3 MOSFETs on your board, turn them on. It would work the same as the tricolor LED on your board. It would just light up the whole room. So I think that's it. People have questions? Otherwise, hopefully this helps for Gadget 1.
I want to talk to you about grading. Okay, so that's